need to still do this because you want to see whether your process is within control or not. So when you do population, every day we don't do for the entire population the mean and standard deviation. So we do for the process, we get the population mean and standard deviation, and to check whether the process is in control or out of control. So occasionally we need to do the quality control aspect. So we pick up, there's a quality control department, they pick up samples and they try to analyze that. So when they do this at 95% confidence, they calculate like this. All right. So the entire process of analysis, okay, using data is shown in this particular figure. So when you know the population mean mu, okay, so what if in this scenario, let us say you do not know the population mean, mu is unknown. So what we do, we pick up a sample and we calculate the sample mean. So from the sample mean, so that's very important. So you need to pick up the samples in a random fashion. Okay, you need to follow. So the success of your data analysis depends on your samples. So if you pick a garbage samples, your results also will be a garbage result. So you need to follow systematically picking up random samples. So once you pick up random samples from this population and you calculate that the sample mean is 50. So now we apply this 95% confidence interval and we can say that the population mean. So we can comment on the population mean based on sample mean. Okay, so this is part of the statistical analysis. All right, I moved on. So what is the general formula to do this confidence interval estimate is shown here. So we take the point estimate, then we do the plus or minus. So the critical value multiplied by the standard error. So the standard error is, we know that it is sigma over square root of n. When we know the standard deviation of the population and the sample size. So that will be your standard error. So this critical value depends on your confidence interval. So if our confidence interval is 95%, so the value is about 1.96. Okay, so this depends on the confidence interval. If we go for the 99% confidence interval, I think the value will be 2.35 or something. So we can see that. So this is basically the general rule or the general formula to find out the confidence interval estimates for the given sample mean. Okay, so this will be the general formula. All right, I moved on. So confidence interval will contain the unknown population. So confidence level is a percentage less than 100%. So we can see confidence levels at 95% means, okay, when we talk about 95% confidence level, so what is the, we can also write this as 1 minus alpha, okay? So where this alpha is the critical, okay, so this is the critical value, or this is what we are ignoring, okay? So alpha is 0.05. So we can write this confidence interval 95% as 1 minus alpha. So in such a case, this alpha can be 0.05. All right, I moved on. Okay, so when we do the confidence interval estimates, so there are two scenarios for population mean. One is when we know the population standard deviation. When we know the population standard deviation. So first we look into the calculations related to when sigma is known. After that, then we go for sigma is unknown. So the same type of calculation can be done for the other characteristic variable, which is population proportion. Okay, so when confidence interval for mu, when sigma is known, so when the standard deviation of the population is known, okay, when sigma is known, so the expression for confidence interval estimate will be so when sigma is known, we can use the confidence interval estimate by this expression. Please note down this equation. Okay. So whenever we are dealing with confidence interval estimation based on sample size and sample mean, and when sigma is known, the standard deviation of the population is known, then we use this formula. So here we are calculating the z value at alpha over 2. Okay, so this alpha over 2 is the probability value for in each tail. So in each tail means, so again, we can look at the probability distribution. So when you're looking at 95%, okay, so this side lower tail, there will be 0.025. And upper tail also, we are leaving out the 0.025. So the alpha refers to this, alpha over 2 refers to this 0.02. So this is for 95% confidence interval. When sigma is known, how to calculate the interval estimates. Okay, so for 95% confidence interval, the z value is given as 1.96, you can see. So this is the z value for 95% confidence. Okay, so that means alpha by 2, you can see as I was trying to draw earlier. So alpha by 2 is, this is above the limits. So this is the lower confidence limit below, and this is the upper confidence limit below. So that means whatever you see in green here is the 95% confidence interval estimate. Okay, and for this, the critical value is plus or minus 1.96. Okay. So this table basically lists what will be the critical values when we have different confidence intervals. Out of this, most of the time we will be using 90% or 95% or 99%. So these are the three values which most of the calculations require. So you can just note these values for okay, when you note down these values and when you know, there will be no need for you to look into the probability tables. Okay, and yeah, most of the time you will have either 95% or 99%. So these are the two significant confidence interval estimates. Okay, so for 95%, we use the critical value 1.96. So for 99, it is 2.58. All right, I move down. Okay, so this is basically tells you when you do at 95% confidence, okay, the interval is extended from, so X bar, this is the sample mean, minus the critical value for 95%, that is Z alpha over 2, then the standard error, which is sigma over square root of n. From this is the lower estimate to the higher estimate. So where you are adding the mean plus this critical value for 95% confidence and standard error, sigma over square root of n. So the value 95% confidence interval extends from x minus this to x plus this. All right. So you can appreciate this once we go through some calculations. Okay, let us look at this example. Now, this example says that in a sample of 11 circuits from a large normal population, which has a mean resistance of 2.20. So here the mu is given as 2.20 ohms. So this is the resistance, okay? This is the mean resistance of the population. Okay. So we are picking up a sample size of 11. Now for this process, the testing says the population standard deviation is known, and the sigma value is known here, which is 0.35. So sigma is the standard deviation of the population. So mu is the mean of the population. So and sample size is 11. Okay. So now for this data, we are asked to determine at 95% confidence interval. So what will be the true mean resistance of the population? So what is that you can say at 95% confidence interval? So all the required data is there. So what we need to do is just pick up the formula and do the calculation. Okay, so we write down at 95% confidence interval. So this is our formula. So x bar plus or minus the critical z value multiplied by the standard error. So standard error is sigma over square root of n. So x bar is, let us say, I think it is given as the sample mean is given as 2.20. So if the sample mean is given as 2.20, then for 95% confidence, the critical value z is 1.96. So sigma is the standard deviation for the population, n is the sample size. So once you do this calculation, now you can see the result is the population mean will be between 1.993 to 2.4068. So that means you will be confident at 95% confidence interval, okay, that the population mean will lie between these two values. That means 95% of the samples you pick up from the population, the samples can be different, okay. You can be certain that the mean will lie between 1.993 to 2.4068. All right. So that is the interpretation of this confidence interval. Okay. So what is the interpretation is listed here. So we are 95% confident that the true mean resistance is between these two values. Okay, lower value, upper value. And though the true mean may or may not lie in this interval, but we can say that the 95% of the samples taken from the population will contain the true mean. All right. So we have looked into when sigma is given, okay, when the standard deviation of the population is known or given. So the next alternative is when the standard deviation is unknown. When the standard deviation is unknown for the population, and most of the time this is the case. Okay, we may not be knowing the standard deviation and the mean for the population. So when the standard deviation is unknown, now how to calculate the confidence intervals? So for doing this, okay. So because most of the time we may not be knowing the population standard deviation. So in this case, I will say, I'll just go to the expression. So mathematically, we can calculate the interval estimate using this problem. So here you don't find the z value. So this z distribution is required when you know the standard deviation. Okay, when the standard deviation is unknown, so we use the t distribution. Okay, so here we are coming out with another data. Okay, probability tables, but here the probability tables are for t distribution. So t distribution means where you have no idea on the sample standard deviation. So when you are not aware of the sample standard deviation, now how we do, we can calculate the sample mean from the given data. So if you pick up the samples, okay, we know the sample size n, okay, you can calculate what will be the mean of the samples. Then we can also calculate what is the standard deviation for the samples. So here, please note, we are not using sigma. So sigma we use for population. So here we are using S. So S is for the sample. So we can calculate S if we know the sample size and sample data. So now here the critical value is not the Z critical value, but it is another critical value known as the T distribution. So now we have another set of tables which is given for the students' T distribution. So why it is called a students' T distribution? Mainly because I think the statistician who put forward this theory, he published the results under his pen name, which is student. So it was a student, that was his pen name under which he published this paper. So this is this distribution is popularly known as the students' T distribution. All right. So we require this distribution when the population standard deviation is not known. When sigma is unknown, we have to use the T distribution. So we have Z distribution tables and we have T distribution tables. All right. So please note down this formula. So this formula is when sigma is unknown. All right. So when you calculate the T distribution, the critical value for T distribution, so what is required is the sample size, okay? And we need to know the degree of freedom, So this degree of freedom is nothing but the sample size minus 1, n minus 1. So that is the degree of freedom. So if your sample size is 25, the degree of freedom is 25 minus 1, so 24. So to know the T distribution tables, so the sample size is required, and subtracting 1 from the sample size, we can identify the degree of freedom. All right. So I move down. So the degree of freedom is n minus 1. So once you know the degree of freedom, then how to calculate? Okay, this slide basically explains why the degree of freedom is n minus 1. Okay, just to understand why it is n minus 1. So we know that if we know the mean of 3 numbers is 8.0, let us say, and you know one number is 7, the other number is 8. So what will be the third number? So when the mean is 8, okay, the total of the 3 numbers will be 24, right? 3 into 8 is 24. So when the sum of the 2 numbers is 15, so x3 will be 9. So you can change x3 value. So what you can play with x1 and x2. So therefore the degree of freedom is 2. Okay. So therefore the degree of freedom is no, because x3 value will be fixed. So you can only change x1 and x2. So when the sample size is 3, the degree of freedom will be 2. When you have 25 samples, then the degree of freedom will be 24. Okay, so what is the relationship between this t distribution value and this z distribution value? So we can see that as the sample size increases, okay, from the slide you can see, as the sample size increases, the t distribution value tends to z distribution values. So this is for large sample size. Okay, they tend to same. Okay, the t distribution tend to give you the z distribution value when the sample size is very large. So what you see in this particular graph is that when the degree of freedom is low, that is your sample size is only 6, you can see the curve is very flat. Okay, so the red curve is spread over a long distance. When the degree of freedom increases from 5 to 13, you can see the distribution curve is rather sharp. Now, as you keep on increasing the sample size, so the curve looks very close to the standardized normal distribution curve. Okay, but most of the time we will not be having large sample size, so therefore we may have to do the t distribution calculations. All right, so this is how the student's t table looks. Okay, so the first column in the student's t distribution will be the degree of freedom. So this column is the degree of freedom. Okay, different tables will give the values differently. Now, for example, degree of freedom, many tables will give you up to 50, 60, but some tables can give you up to 1000. Okay, so it all depends on, what type of student t table you are using, depending on your sample size. Okay, so the rows are given in terms of the upper tail areas. So that means here 0.10, 0.05, 0.025. So it goes on. Now, how to use this? So when our sample size is 3, okay, the degree of freedom is 2. Okay, and if you are looking at alpha is 0.10, so when you are looking at 90% confidence interval, so your alpha over 2 is 0.05. Okay, alpha is the critical value here. Alpha over 2 is 0.05. So now to do the t distribution value for a degree of freedom of 2, and when your upper tail alpha over 2 is 0.05, so you can pick up this value. So your t distribution value is now 2.920. Okay, so what you can see is here the table values contains, okay, t values, not the probability values. So the probability values are shown in the top row. So the top row only contains the probability values. So for all the other values are not probability values, t distribution critical values. All right. Okay. Now you can see here the t distribution values, how they tend to be towards the z distribution values. So when you're looking at confidence level of 80%, when your sample size is 11, that means for a degree of freedom of 10, so the t distribution value is 1.372. Okay, whereas the z value is 1.28 for this. Okay, but when you increase the sample size to 21, okay, so the value reduces from 1.37 to 1.325. And it further reduces when your sample size is 31 to 1.31. So you can see that as the sample size increases, okay, the t distribution values trend towards the z distribution values. Okay. This is only of academic interest only, just to relate the t distribution values with z distribution values. All right. Okay, I clear this, then move forward. Okay, so now let us look at this example to appreciate further the how to use the t distribution values. Okay, let us go through this example. So a random sample of n is 25. So the sample size is given here 25. Okay, so n is equal to 25. So the mean of this samples is 50. So we can calculate the mean from the samples, right? And we can also calculate the sample standard deviation. So in this case, it is 8. Okay, now you're asked at 95% confidence interval, find the value range for the population mean. So we need to find out the range for the population mean at 95% confidence interval. So now we identify what is the degree of freedom, n minus 1. So degree of freedom is 24. We can't use the z distribution tables because we have no idea on the standard deviation of the population. So what we know is only standard deviation of the sample. Okay, so therefore we have to use the t distribution tables. So now because it is given as 95%, so the critical value is, we have to look for alpha over 2. Okay, alpha is 5%, alpha over 2 is 0.025. So we have to look for, from the tables for the probability of 0.025. Okay, so if you look at the table for the degree of freedom of 24 and look for the probability of 0.025, the critical value, then the t distribution table will give you the value of 2.0639. Okay, so this value we can read from t distribution tables for a degree freedom of 24 for a critical t value of 0.025. So then we can write down the confidence interval. So it is x bar plus or minus the critical t value multiplied by the standard error. So sample standard deviation over the square root of the sample size. So we know we can read this value 2.0639 from the t distribution tables. So if you do this calculation, then you know that the range for the mean for the population will be as shown here. Okay, so you can see the value of the mean varies between 46.698 to 53.302. So the lower limit is 46.698 and the upper limit is 53.302. So based on a sample size of 25 and by measuring the mean of the samples and by measuring the standard deviation of the samples, now we are commenting on the population mean at 95% confidence interval. Okay, so in this particular example, we are using t distribution because we have no idea about the standard deviation of the population. Okay, so the interpretation is very similar to what we have done for the population mean for the z distribution when sigma is known. Okay, again, we need to know what are the requirements to do this confidence interval estimation. So the requirement is again that the distribution should be normal distribution. Okay, and you can check the distribution, population distribution, whether it is normal or not by doing the mean median, by calculating the mean median, and also by plotting this 5-member plot. Okay, the box plot. Generally, you will not be asked about this confidence the shape of the probability distributions. So what is important is applying the confidence interval estimates. So to speak about the population mean.
So
yep.
The table itself has a one tail, two tail. Sorry, how do we figure this out?
Yeah, we'll be looking some examples for one tier. One tier means one side. Two tier means both sides. So you have to just multiply it through. Okay. So now, so far we were calculating the confidence interval estimates. We have done when sigma is known. So when sigma is known, we use the critical value for z. Okay, it's for z. So you can use the critical value estimates for z. When sigma is unknown, then we have to use the student t distribution. Okay, so we have to use the student t distribution by knowing the degree of freedom. Okay. So now we can proceed for another characteristic, which is not mean, but which is proportion. So in the last session, we looked into the meaning of proportion. So many times from the data, there's no way you can calculate mean. Okay. So as we discussed, when in a game, you win 20 times and you lose 40 times. You can't define what is mean, but you can say what is the proportion of your choice of winning. Okay. So proportion is another type of characteristics which we can calculate for our data sets. Okay. So when we use this variable proportion, again for population, we use the symbol pi. Okay. So for population, the symbol used for proportion is pi, and for sample, we use p. So for the sample, the proportion symbol is p. So don't get confused this p with probability. The unfortunate thing is, in some cases, we use p for probability. But in this particular scenario, when you are talking about proportion, for population, the symbol for proportion is pi, and the symbol for sample proportion is small p. All right, so I moved on. Now, when you're doing this proportion, the standard error for the proportion, we can write it as sigma p. So the standard error for the standard deviation for the proportion is sigma p. So you calculate pi into 1 minus pi over n. So in the last session, we have looked into this expression, okay, this equation. So this is how we can calculate the proportion for the standard deviation for the proportion when you are picking up a sample. Okay, n represents the sample size. So this is based on the central limit theorem. So based on the central limit theorem and based on the concept of sampling distributions. So when you're dealing with sample data, so this one is when you are dealing with population data. So this formula is for population data, and this formula for standard deviation is for sample data. Because for sample data, we use P for proportion. Okay. Otherwise, you can see both the same. So there's no difference between the formulas. Okay, the symbol is different. The pi symbol is for proportion, for population, and the P symbol is for population. All right. So now when you're calculating this, but the characteristic of proportion, again, the confidence interval estimates will be based on the z distribution. So this is the critical z value. Okay. Again, depending on the confidence interval, we can find out this value from the tables. So again, if you are looking at 95% confidence, so the value will be 1.65. So again, you will have this plus or minus. So this is the sample proportion plus or minus the critical value multiplied by the standard error or the standard deviation for the sample. Okay, so this is exactly like the question related to mean, population mean or sample mean. Uh, we are not using mean but proportion. Otherwise, the formula is exactly the same. All right. So there's one simple condition when you're using this proportion. So here it is listed here. So the condition is that n into p, the sample size into proportion, should be greater than 5. And also n into 1 minus p should be greater than 5. So because if this is not valid, so then there will be errors in the calculations. So to make sure that this formula is valid, so first we need to check whether from the given values, n into p is greater than 5 or not. And also n into 1 minus p is greater than 5 or not. Okay, so this is again a theoretical thing, and most of the time, because our sample size is large, so this condition is valid. All right, now let us look at the example here. So you pick up a random sample of 100 people shows there are 25 people are left-handed. So from a sample of 100 people, so you estimate that there are 25 people are left-handed. Now, if I ask you what is the mean for this data, so there's no sense for that variable. So for here, we have to do the proportion. So out of 100 people, so what is the proportion of left-handers? Okay, so you can calculate the proportion P, which is, okay, 25 out of 100. Then you at 95% confidence interval, you are asked to find out, so what will be the true proportion of left-handers? Okay, so we have only the sample data of 100 people. Out of 100, 25 are left. So therefore, we know what is the proportion. So the proportion is 25 over 100 or 0.25 for the samples. Okay, and the sample size is 100. And the confidence interval estimate is at 95%. So therefore, we can apply. Okay, so we can apply the formula here. So the formula is the proportion plus or minus. Okay, plus or minus is okay to know the range. Then this is the critical estimate for the 95% confidence. So the value is 1.96 for 95% confidence. So multiplied by the standard error. So this portion is the standard error. So what is P? P is the proportion, 0.25. So we get 0.25 just because there are 25 left-handers out of 100 sample. Okay, so 25 over 100 will give you the proportion. So P is 25 over 100, which is 0.25. All right, so what is 1 minus P? So 1 minus P is 0.75. Okay, so the standard error is P, that is 0.25 multiplied by 1 minus P. So 1 minus P is 0.75 over the sample size 100. So if you do this calculation, add and subtract, so you will get the value for the proportion of the population. Okay, so we can say that at 95% confidence, we can say that the proportion of left-handers for the entire population will be between 0.1651 to 0.3349. Okay, at 95%. In other words, we can say that you pick up any number of samples from the population. Okay, 95% of the samples will contain the population mean with a population proportion between these two values. All right, so this is how we can estimate the proportion for populations based on the sample data. All right. So the interpretation is the same thing. Okay. So we are 95% confident that the 2% of left-handers in the population is between, okay, the lower limit of 16.51 and upper limit of 33.5. Okay. Other way to interpret this value is that 95% of the samples collected from the population. So we'll have a population proportion of these two values in between. All right. The next calculations are based on how to find out the minimum sample size required. So to apply this confidence intervals. So determining the sample size. So whether the sample size chosen by us is correct or not, or what type of sample size is required. Okay. So again, this we can do the calculation for both the mean and for the proportion. Okay, so there are two more equations for under this we can see. All right, so we need, I think somebody is using the mic. All right. Yeah, I think Sharmini was asking a question whether Z value is always plus or minus 1.96. Yes, that is always plus or minus 1.96.
Must it always be too significant level? Because based on the table, right? When you said 90% is 1.65, but on the table itself it's 1.645.
There's very little difference because it's rounded off.
So it doesn't matter that it's too significant.
For critical values, always use 2 digits. Okay, so now to find out the sample size, what is required is this margin of error, which is written as E. So the margin of error is E. So we need to know this E. So this is related to the level of confidence, that is 1 minus alpha. So the margin of error, this E, is also called the sampling error. Okay, so we can calculate the sample size when we have some idea about this sampling error. In other words, when the sampling error is given, then we can calculate the sample size. All right, I moved on. So you can see how we can derive the formula for the sample size from here. Okay, so we know that for the mean, this is the confidence interval estimation. So we use this formula for confidence interval estimation. So here the standard error refers to the one which is circled in red here. So this is the standard error E. So standard error E is the multiplication of the Z critical value over standard error. Okay, so if you multiply these two things, that will give you the sampling error. Now this sampling error, or we also call this margin of error. Now once you know this E is equal to this formula, now you have to derive what is N sample size from this. So what is the N value from here? So how we can calculate N value from here? So because there is a square root here, we can square both sides. So taking the square both sides and simplifying the equation, then we can find the expression for the sample size as shown here. So we can derive from the sample error, the sample size formula will be like this. Let me tell you, there will be 5 marks question where you will be applying this formula. So calculating the sample size when the error is given, sample error or marginal error is given, okay, you have to simply use this formula. And again, this is related to the confidence interval. So the Z value related to the confidence interval. Okay, sigma is the standard deviation for the population and E is the error. So for most of the calculations, the value of the standard error will be given to you. Okay, so this is for the sample size for the mean. So similarly, we can also give the formula for the sample size of the proportion. Okay, now let us say there's an example here we can go through. So when sigma is 45, so standard deviation for the population is 45. So what sample is needed to estimate the mean within plus or minus 5? Okay, with 90% confidence. So here this marginal error or sampling error is given as 5. So E is 5. Okay, and since you are looking at 90% confidence, so the value for 90% confidence is 1.645. Okay, standard deviation is given. So you just put everything into the equation and calculate. So you will get a value of 219.19. So because the sample size is in whole numbers, so we'll give the next higher number. So after 219, the next higher number is 220. So that means you need to have a minimum sample size of 220 when you are looking at 90% confidence, when your sample or the marginal error is plus or minus 5. Okay, so it is a simple calculation from the formula. All right. So the next we look when the sigma is unknown. Okay, how to determine the sample size now for the proportion. Okay, so determining the sample size for the proportion. So now you can see for the proportion, the formula is slightly different. Okay, so we take the critical value of Z, square of that, then pi is the population proportion. So population proportion into 1 minus population proportion over the marginal error square. Okay, so to calculate the sample size for the proportion, so we need to use this expression. So the good thing is that all the values will be given except this one, the Z value. So depending on the confidence interval, you need to look the probability tables and find the Z value. And as we were discussing, there are only 3 possibilities: 90%, 95%, and 99%. All right. So let us see if there's an example. Yeah. So there's an example you can see here. Now, how large a sample would be necessary to estimate the true proportion of sales invoices containing errors in a large population with plus or minus 7% error. Okay, so this is the error percentage given. Now you're looking at 95% confidence. Okay, so now you are asked to assume a sample proportion of 0.15. Okay, so now we need to calculate the sample size and for this scenario. So what is the sample size? So we can apply the formula. Okay. So the only thing here you see is there is an error in the slide. Okay, so this one should be 7. Okay, because error is given here 0.07 and it is typed as 0.03. Okay, so please take note that it is not 0.03, but it is 0.07. So for the critical value for 95% confidence, we are using 1.96. Okay, the population proportion is given, okay, 0.15. Then 1 minus the proportion, okay, 1 minus 0.15 over the error square. So error square is 0.07. So it is 7%. 7% represents 7 over 100. So that is 0.07. So you get a value of 99.96. So we round it up to 100. So there will be a minimum sample size of 100 required so that you can estimate the confidence interval with a marginal error of 7%. All right. Ethical issues is part and parcel of all statistics. So whenever we talk about ethical issues, so you must make sure that you are not hiding the data. Okay, you are using the samples randomly. You are not picking up or you are not selecting the sample. Okay, so you need to follow and you need to represent all the results. You need to tell what is your sample size and how your sample is selected, things like that. You need to take note of this point when you are doing your assignment. So while doing your assignment, so give a clarification on your data, how your data was selected. Okay, that is to score full marks. Otherwise, because ethical issues not discussed, so we deduct 5% or so.
So for the marginal error, let's say if we're doing a research, do we decide the marginal error percent, like 0.07? Do we decide it ourselves?
Yeah, you can estimate yourself what will be the error that which can be tolerated. Okay, so the summary in this case is quite simple. We have done how to calculate confidence interval estimates when the standard deviation is known. Okay, when the standard deviation sigma is known, we use the normalized standardized Z distribution tables. When sigma is unknown, then we can use the student T distribution tables. And we can also calculate the confidence interval estimates for proportion. Okay, after that, then we have seen how to calculate the sample size required if we know the margin of error. So when the margin of error is known, then we can calculate the sample size required either for the mean or for the proportion. All right. So with this background, then let us do some examples. Okay, guys, let us do this calculation yourself. I'll wait for your answer. I'll pause here for a minute. So the mean is given 85. The population, the sample size is 64. And you're asked to construct a 95% confidence. Sharmini is asking about should we round n to the nearest integer or the nearest higher integer? Always the nearest higher integer, Sharmini. Okay, it should be always the higher integer. All right, guys, those who are online, give me the answer for this question. Is given. So calculate the 95% confidence interval estimate. For the proportion mean, I think this should